Okay, this is statistics, basic statistics. We're looking at chapter 5 on probability distributions. So let's jump in. In a discrete probability distribution, we have a list of values that random variable can assume. All right, so let's look at the example. Suppose that we toss a coin 3 times in a row. Let x be the number of heads in the 3 tosses. So first, let's take a look at the sample space. Remember, sample space is a list of all possible outcomes. We did this with tossing it 3 times. Heads, 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 tails, heads, tails, heads, 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 tails, 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 heads, tails, heads, tails, heads, tails, tails, and all tails, 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 tails. All right, so that's our list of our sample space. So 8 possible outcomes, 1, 2, 3, 4, 5, 6, 7, 8. And now let's do a discrete probability distribution. So x is the number of heads that could happen. So let's see, we could get no heads at all. That would be 0. 1 heads when you flip it 3 times, 2 heads, or all 3 heads. And then p of x, that's the probability of each one of those occurring. So since we have a list of all possible outcomes right here, we can just base it off of the sample space. So the probability of getting no heads at all, well, that only happens 1 time out of 8. So that is the probability, is 1/8. 1 heads. So let's see, that happens here, there's 1 heads, there's 1 heads, there's 1 heads, that's 2 heads, 2 heads, 2 heads, and that's all 3 heads. So 3 times out of 8. 2 heads, let's see, that happens, heads, heads, 2 heads, 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 heads. That happens also 3 out of 8. And then all 3 heads, that only happens once. Heads, 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 1 out of 8. And so when we look at this, the probabilities of all of these should always add up to 1. So if I added 1 plus 3 plus 3 plus 1, that's 6, 7, 8 eighths, which is 1. All right. Okay. So let's take a look at another example. Suppose the probability that a customer will purchase 0, 1, 2, or 3 books is 45%, 30%, 15%, and 10% respectively. Construct a probability distribution for the data. Also find the probability of a random customer buying 1 or 2 books. Okay, so let's do that. Go into the bookstore. Probability you buy none, you just look, 45%. Probability you buy 1, 30%. Probability you buy 2, 15%. Probability you buy 3, 10%. So that is our probability distribution. But now let's find the probability random customer buys 1 or 2 books. 1 or 2 books. And so that's going to just be, or means add. Remember, or means add. So that's just going to be 0.3 plus 0.15. That's going to be 0.45. So 45% chance they buy 1 or 2. All right. I'm going to add that to the notes, probability. Okay, let's look at the next one. always should add up to 1. Each value of a random variable must have a value between 0 and 1 inclusive. So that means it could be 0. It could be 1, 100%. All right? So let's take a look at the example on the bottom of the first page of the Chapter 5 notes. All right. So that is 1, 2, 3, and 4. And 0.24, 0.33, 0.02, and 0.45. So if we add all of those together, 0.24, 0.33, 0.02, and 0.45, we add that all up, that adds up to be 1.04. That means this doesn't add up to 1, so this is not a probability distribution. It looks like 1, but it is not. It always has to add up to 1. There could be round off error if it went out like 3 places, but it would be like 0.99 or something. It wouldn't be that. So that is not a probability distribution. Let's look at the next one. This is also an example of not a probability distribution. It looks right on the surface, but if you look really carefully at it, this should be a big old red flag. You can never have a negative probability. The probabilities have to be between 0 and 1 inclusive. 0 means it's impossible, 1 means it's 100%. And so you can't have a negative probability ever. So that isn't a thing. So this one is also not a probability distribution. Let's look at one that is. What if I tell you it is a probability distribution, but we leave a little piece of information off. So we give you 1, 2, 3, and 4, and we give you the probabilities. We can tell you 0.24 and 0.02 and 0.45, but then we don't tell you what that missing one is. Well, you can find the missing one. You just add up the 0.24, the 0.02, and the 0.45. So add up all the other probabilities, put those together. And since we're only missing the 1, we can figure that out. So 611, carry the 1, 6, 7, so that's 0.71. So if you just do 1 minus 0.71, that's 0.29. So that one is what, 2? 2 has to be a 29% chance, 0.29. All right? Okay. Let's take a look at mean, variance, and standard deviation. Ooh, and like an expectation, like expected values. Let's take a look at those. All right. So when we're looking at those, we've got, let's look at the probability distribution. So they give us a probability distribution again. So this is 5.2. Pages and the notes. Oh no, I didn't mark the pages in this one. That's just page 2 in the chapter 5 notes. All right. So let's take a look. We've got X is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and then the probabilities of X. 0.1, 0.05, 0.05, 0, 0.1, 0.05, 0.5, 0, 0.05, and 0.1. All right, so if I want to find the mean of this, that's also known as the expected value. And so the expectation. Let's take a look at what that is. Here, did we make up a scenario with this, or is it just, if a person randomly is chosen to select a number from 1 to 10, these are the probability distributions. Okay, so the expected value is also known as the mean. To find the mean, now all of these don't get equal weight. Normally, think about how we find the mean. We add them all up and divide by how many there are, right? But these aren't all equally as likely to occur. So we can't just add them all up and divide by how many there are. We have to work these probabilities into our calculation. Since 7 is 50%, that's a very likely scenario. Since 4, nobody ever picks, that's 0. So that doesn't impact it at all, the mean, nor does 8. All right, so what we do is we still want to find the sum of all of these. But what you do is you find the sum of each value times the probability of that occurring. So to find the mean, we're just going to take 1 times 0.1 plus 2 times 0.05 plus 3 times 0.05 plus 4 times 0 plus 5 times 0.1 plus 6 times 0.05 plus 7 times 0.5 plus 8 times 0 plus 9 times 0.05 plus 10 times 0.1. And when you multiply all of those out, you end up with this. 0.1 plus 0.1 plus 0.15 plus 0 plus 0.5 plus 0.3 plus 3.5 plus 0 plus 0.45 plus 1. So now look, what one had the most impact was that 7. 0.5 times 7 was 3.5. That is the lion's share of the mean. That one contributed the most to making up this mean. So when we add all those together, we get 6.1. That is the mean or expected value. So let me change the scenario on this same problem. Let's say that you were gambling and you would write a check for $1 or $2 or $3 or $4 or $5 or $6 or $7 all the way up to $10. All right. So they pull a token out, and depending on what token they get, you write them a check for one of these denominations. So apparently there are none for $4, there are none for $8, so you're never going to pay that. But the expected value is the expected payout in the long run. So if you wanted it to be an absolutely fair game, you would charge to play what the expected payout is. So if the expected payout is $6.10 on a game of chance like this, that's what you would charge, and then it would be a fair game. That's usually not how gambling works. In fact, that's never how gambling works. It's always, they figure out the expected value, and then they maybe charge you $10 to play this game. So every time you play, they're basically making $4 off of you. And, that's how gambling works. Or maybe not that, maybe $1. Let's say they charge you $7 and they say, look, there's a 50% chance you're going to win back your $7, or you could win 9, or you could win 10. And, that's how they get you with that. But the expected value is the expected payout in the long run. So that doesn't mean somebody could pick one right off the bat and get $10. So they paid $7 to play, and then they win and get $10, and they just walk away. And you're out, if you were running the game, you're like, oh boy, it's in the long run. If somebody plays 1,000 times, the average payout will be $6.10. So that's I think an easier way to think about what expected values are. All right, let's take a look at the next page, the third page, page 3. So let's say St. Anne's raffle. Each ticket costs $50 and only 10,000 tickets are sold. There is one grand prize of $300,000, 10 first prizes of 1,000, and 100 second prizes of 100. Find the expected value of a random lottery ticket. Okay, so let's take a look. I think I'm going to need the whole board for this one, so erase this example. So we are talking about winning on this one. So these are going to be weird amounts. All right. So look, you pay $50 for a ticket. So that means if you win the grand prize, you didn't really win $300,000 because you paid $50 to play. So that means you actually won $299,950 because you paid $50. All right. Same with the other ones. Look, if you win 10,000, oh no, 10,000 tickets are sold. 10 first prizes. If you win $1,000, you don't really win $1,000 because you paid $50 to play, so you win $950. And if they give you $100, but you paid $50 for the ticket, that means you win $50. And if you don't win, that means you're out $50. All right. Okay. So they sold 10,000 tickets. The probability that you got the winning ticket is 1 in 10,000. Because they only give away one grand prize. But you could also win 950, right? There's 10 of those going out. The $1,000 payouts. $100 payouts. There's 100 of those going out. And then this is the most likely scenario. Look, how many ways can we win this game? There's 110 plus 111 ways to win, right? They're paying out for $100 100 times. They're paying out $1,000 10 times. And they're paying out $300,000 once. That means there are 111 ways that you could win this game. There are then, let's see, 10,000 tickets minus 111, the winners. That means the rest are losers. So there's 9,889 losers out of 10,000. So that's how we got that 9,889 up there. It's the complement of the winning would be the losing, right? If you didn't win, you lost. So let's find the expected amount on this. So we'll see if it's a fair game. So if this breaks out to be 0, then that would be, or not 0, 50. Then it would be fair. So let's do x times the probability of x. So that's going to be 299,950 times 1 over 10,000 plus 950 times, we could reduce that, we could kill a 0 in each one, 1 over 1,000 plus, again, we could kill 2 zeros, top and bottom, 50 times 1 over 100, and then this is the big one, plus negative 50 times 9,889 over 10,000. And so when we work that out, that's not very good. Let's see here. This is 29.995 plus 0.95 plus 0.5 plus negative 49.445. That's negative 18. That's a negative value. So if it were a fair game, raffles usually aren't fair games. They're to raise money for something. And so, yeah, it's not a fair game. The average payout is negative 18. That means, yeah, you're likely to lose $18 per ticket on average. So you're going to be out the $50 if you don't win, if you're not one of the 111. But on average, over the 10,000, the payout is negative 18. So that means they're up $18 every time. That's how you figure out how much money you're making. I mean, you could also just do it with raw numbers in this scenario, where you figure out what the payouts are. All right, let's look at another example. Suppose you choose, you have a choice between investing in 2 bank bonds. The first bank pays an interest of 4%, but has a 2% chance of going completely belly up, where the second bank pays 2.5%, but has a 1% chance of defaulting. Which bond would be the better investment? So we would set up 2 different problems and work them both out and look at the expected value. And whoever has the higher expected value, that would be the one you'd want to go with. So let's take a look at that problem. So we have X 1.04. So if it pays 4%, you put 1.04. That means your money and then plus 0.04 times your money. Or you lose all your money, 0. And so the probability of that happening on the first bank was 0.98, which means there's a 2% chance it'll go belly up, and 98% chance it'll be just fine. The other bank, it looks like this. It's only 2.5%, so that's 1.025. Or 0. If it goes belly up, there's only a 1% chance of that going belly up. 99% chance that it doesn't. So if we are weighing these 2 as which one is riskier, we look at the expected values. So the expected value of this one is 1.04 times 0.98 plus 0 times 0.02. And so that ends up being just this, 1.0192 plus 0, so that's just just about 1.02. So it's about a 2% payout. So let's take a look at this one. The expected amount would be 1.025 times 0.99 plus 0 times 0.01. So that, when we multiply that out, we get 1.01475. So it turns out, let's see, we'll call this one bank 1 and this one bank 2. The first bank is better. Because look, it's 1.019 and this is 1.014. So this one actually has a slightly higher expected value, and so that's the one that we would go with. All right. Okay. Outstanding. I'll do 5.3 on the next video.